Hello everyone, thanks for the introduction, Lim. I guess you can now see my screen, right? Great. So, thanks for the introduction again, and thanks for the invitation. I'm actually going to talk to you about work that was performed in the framework of Sanjit Parekh, who is a former PhD student of mine. We co-advise him with Alexei, Nyok, Patrick, and Gaël. And the goal here, I need to move this back, is to identify, locate, and separate music instruments in audio and visual modalities. Okay, so in this example that you see, this would mean being able to detect the presence of the violin, possibly separating it from a noisy background, while also locating it both in time, so that is giving the start and end time in the audio, and providing a bounding box for the violin on screen. Okay, the task can be actually quite challenging, especially due to the potential asynchronicity of the audio and visual appearances in the video, right? So that means you can hear the violin without it being visible on screen, and vice versa. Okay, you can see some violin on screen and it's not the instrument which is played. And also the other challenge is we want to be able to perform this using only weak video document level labels. Okay, so no particular annotation across time. You don't know when the instrument is going to play exactly, or where it's going to appear, at which point in time and where in space. So you just know that at some part of the video there's a violin playing, to stay on this example. Okay, and with that you want to be able to train a system that's able to identify, locate, and separate the sound of that violin and its appearance on screen. So our approach to this problem adopts the idea of multiple instance learning, as in previous works in computer vision, for instance, on object localization and classification, where multiple instance learning strategies have been particularly embedded in CNN architectures. The main trick being the use of so-called region proposals, that is, candidate bounding boxes for the objects to be detected. And the problem then amounts to jointly selecting the right bounding box and classifying the object enclosed. Similar problems are now more and more being addressed in the machine listening community, where especially thanks to the VCase initiative and the introduction of large data sets, such as the audio set, we're seeing interesting progress towards audio event detection using weak labels. Also actually following the deep multiple instance learning approach, where we've seen a lot of proposals using attention-based methods in particular. Another source of inspiration for this work is research along the line of multimodal deep learning, where a couple of interesting architectures have been proposed that we could roughly divide in two categories. First, the so-called two-stream architectures, where modality-specific representations are learned in separate branches of a network before being combined at the decision level, which we should oppose to what can be referred to as cross-modal architecture, where the objective is to predict one modality based on the other, say the audio using the visual input. So put simply, the recipe we propose is propose and learn, where each video is considered to be a bag of class-agnostic audio and visual proposals. And the deep network is trained to score each proposal according to its relevance for a particular class. So using a two-stream architecture as depicted here, where each modality, the audio on the one hand and the image sequence on the other hand, is fed to its respective feature extraction and scoring networks, before the scores of both networks are combined to produce a global decision. So both sub-networks have roughly the same architecture, as you can see, that is extracting class-agnostic proposals, learning features, and using them to perform proposal scoring and aggregation. Let's see how we can instantiate this general framework. More concretely, this is the architecture we've devised for this particular work, where we're interested in musical instrument classification and extraction. So the first step is the proposal generation step. On the image sequence side, we generate up to 10 proposals per frame at a rate of 1 frame per second, using a technique called edge boxes. Roughly, the idea here is to consider regions with many edges as good candidates to become proposals. And for now, for the audio, the proposals are merely obtained by extracting, a regular representation, MEL spectrogram representation, and chunking it into roughly 1 second long frame sequences, simply by sliding a window over the signal. Okay. For feature learning, we use well-known networks. So the base visual features are extracted using CafeNet with pre-trained ImageNet weights, adding this 6x6 region of interest pooling layer, and fine-tuning the fully connected layers simply. And for the audio, we fine-tune the whole VGGA network, which has proven to be quite effective for general machine listening tasks. Next is the proposal scoring phase, which consists of parallel classification and localization streams performed in the same way on both modalities. So we can look at the audio modality, for example. And what we do is pass the feature representation through linear fully connected layers and parallel for classification and localization. Okay. So on the localization stream here, a softmax operation is used so as to promote the most relevant proposals for each of the classes. That is, promote in particular here the most relevant temporal segments for each class. And so the classification stream output is then weighted simply by the softmax output, hence performing a soft selection of proposals for each class. So class scores over the whole recording are then obtained by summing the resulting weighted scores over all the proposals across time and space. And so the same is done for both audio and visual proposals. And the video document level scores across the whole duration from both the modalities are simply added after they are L2 normalized to ensure a similar score range. Okay, this is the sum that's computing a form of late fusion. Now we also consider an extension of the audio proposal mechanism, that simple mechanism I just described, where we're using just temporal segments. And we do this with a view to improving the robustness to noisy audio recording condition, and also allowing for source separation. Okay, so source separation becomes as a byproduct. It's not considered as a target. It's not the objective. It doesn't appear, at least in the objective which is being optimized. And the idea is quite simple. That is to decompose the audio magnitude spectrogram by non-negative matrix factorization using K components. Okay, K equals 2 in this example that you see, and use the component signals, so the signals reconstructed from each NMF component, to generate the proposals after chunking them again into 1 second segments. And this is denoted by TKT here. Okay, so K is the kth NMF component, and T is the tth segment in time. And we're going to call these NMF component proposals. The acronym is going to be NCP. Okay. Compared to the previous simpler audio proposal approach, we now have K tracks of segment proposals instead of just one. Okay. What is nice is that a byproduct of this is to allow us to perform source separation. How? Well, simply by aggregating the NMF components using the relevant scores for each class. Well, if we denote by beta KT the score given by the network to NMF component proposal DKT, we obtain a global video level score alpha K, again using max pooling across time. And we can rescale that between 0 and 1. These are the alpha K primes. So these become masking coefficients, okay? And the last step is simply to perform a soft mask-based source and noise spectrogram reconstruction, as you can see here, where SNN obviously refer to the estimates of source of interest and background noise. Okay, that's the main idea. Let's move to the evaluation. We performed it using the kinetics instruments dataset. This is a subset of the kinetics dataset that contains 10-second YouTube videos from 15 music instrument classes. And we're going to look at both classification and source enhancement results. So I'm showing you different variants of the system I just described. This is the video-only variant of the system where the audio branch is completely ignored. So audio is not considered here. These are variants of the audio system, considering the different ways of building those proposals. I'll tell you more about it. And this is the audio-visual variant, that is the multimode variant exploiting both the audio and visual branches. And the first observation which we can make is, okay, without any big surprise, the audio-visual system is performing better than unimodal audio and video, that is image-only systems. That's good, quite expected. And now the other interesting observation is that idea of NMF component proposals seems to be interesting. As we can see, there's some marginal improvement by including them compared to using those simple temporal signal proposals. So, okay, you could say this is marginal improvement, yes, but this is clearly going to give us more robustness. So what we do here is an experiment where we add noise to the audio. So same videos, we just modify the audio track, adding noise at different SNR levels, as you can see here. And now we see that the NCP, the NMF component proposals, become really more helpful, okay? So this is a way of becoming more robust to noise. And again, this is a nice way of very simply obtaining some source enhancement results or source separation results, if we like. And I'm going to show you a quick demo. This is a companion page that you can check later if you like at this URL. I'm going to show you first the visual localization results on some examples, okay? This is what we get for the accordion. These are the bagpipes, cases, guitar, and violin. You see this is working pretty well. Of course, there are some failure cases that you can easily interpret and understand why they are failure cases. The harmonica here is really hardly visible. Here you have a case of visual clutter where it's quite difficult to figure out that there's many bagpipes there. And violin again is difficult here. This is a case of xylophone, which doesn't really look like most of the xylophones we've seen during training. And there's again cluttering. And as I told you, what is nice is you get source separation results. So I'm going to show you this example. This is one video, one test video. Let me first play the mixture. I hope you're going to hear it. I'm not sure I've shared my sound with you, so please let me know if you don't hear the audio. Okay, I guess you got it. I hope you got the audio. And as I described earlier, this is a case where there's that typical asynchronicity where you don't necessarily see both instruments across the whole duration of the video. In the first part, you see the trumpet and then the guitar appears, okay? And these are this is not, I must say, this is not a difficult source separation case. But what is interesting is source separation is just a byproduct. The network was never trained to do source separation effectively, okay? It's just that idea of NMF component proposals that allows us to do source separation if we like, okay? The network was only trained to do localization and classification, but it can also do that. So this is the separated guitar sound. And this is the separated trumpet sound. Okay. Please feel free to check more examples. In a nutshell, we've introduced a flexible multimodal framework for robust audiovisual scene understanding using weak labels. That's the key idea. And there was, in particular, this nice trick of using NMF, an unsupervised technique, to generate audio proposals, which then allows for a more robust audio classification and also for source separation. If you want to learn more about this, please check the corresponding WASPA paper, or better, the long version of it, the journal paper, where there is also other instantiations and some application to machine listening in the context of decays, or even better, the PhD dissertation of Sanjeev. Thanks for your attention, and talk to you later, hopefully to answer your questions.